All right. Welcome, everybody. It's a pleasure to see you all here for our second edition of the Create Sustainability Seminars. It's my pleasure to introduce our second speaker of the series. So today we're going to hear from Carole-Jean Wu, who's a director of AI research at Meta. Over there, she's leading the Systems and ML research team. And she's also a founding member of ML Commons, which is how we connected initially. Carole was also a professor at ASU, and she got her PhD from Princeton and her undergrad from Cornell. Carole has a extended list of awards, including micro topics, best paper awards, and NSF career awards, and many other accolades. So I'm very much looking forward to the talk today. She will tell us about some of the challenges and opportunities on scaling AI in a sustainable way. I really look forward to hear what she has to say on that. So, Carole, the floor is yours. Maybe before we start, I suggest if someone has a question, I am also around to kind of monitor the chat. But Carole, please feel free to tell us however you want to manage this.
Sounds good. Thanks so much for the generous introduction, Juana, and thanks so much everyone for having me here in this sustainability seminar series. My name is Carole, and today I'm going to use this opportunity to share with you some of my thoughts and my work in the space between AI and sustainability, and also where I see our industry is going and what we should be doing going forward. A lot of the work I'm sharing with you is influenced by my research as a computer architect and by my experience now having spent a couple of years in industry developing system infrastructure at scale, and also influenced by my journey through the MLPerf, ML Commons industry benchmark suite that Oana mentioned briefly. So let's get started. You may have read this science paper that was published in around 2020. I think the study was started in 2018, and they were looking backwards on some of the interesting trend in digital technology and data center computing. So in this particular paper, the authors look into how the efficiency innovations in the computing industry has influenced the amount of energy used in data center computing. Between 2010 and 2018, we see that the number of compute instances in global data center has increased by 5.5 times, but the overall energy use for these compute instances only increased by 6%. The authors then projected out that if we continue to innovate in the efficiency space, we should be able to double the number of compute instances in data centers while keeping the overall energy consumptions to be more or less fixed. And that was quite inspiring if you think about sort of putting a lot of our computer system efficiency work into the grand scheme of things. But at the same time, we are seeing such a dramatic growth in artificial intelligence, or AI. AI is touching many aspects of our lives, from science, medicine, entertainment, e-commerce, education, name your favorite application use case. Or at the same time, AI is also advancing many different scientific problems that was just hard to think about a few years ago. For example, at FAIR, we have this Open Catalyst project that is looking into how AI can help us accelerate discovery of renewable energy storage materials. Google has talked about their AlphaFold project, where they use AI to predict protein structures that has the potential to advance biological science domain significantly. And Microsoft has also talked about how AI can be used to improve farming efficiency, such that we can grow food much more efficiently and feed the world's population more effectively. As these new AI capabilities emerge and used to advance the way that we interact, learn, and communicate with each other, we also see that it is driving such a significant growth for data center. Here, I took a look at publicly available data that was published on hyperscaler data center operators from Amazon, Google, Microsoft, and Meta. In the past 6 years, we have seen the overall electricity growth to go quite a bit, from, I guess, the 2.5 times increase for Google to the almost 4.5 times for companies like Meta. Going forward, we expect the energy footprints for data centers to increase for the next decade. They are going to be more populations in the world that will be connecting to the internet. So there is going to be a lot more demand in digital technologies. Also, they are these newer application use cases that we are expecting to thrive, driven by AI or generative AI technologies, among many others. And finally, our computing infrastructure is extremely efficient today. It's going to be even more challenging to make them more efficient in the face of more slowing. There are a variety of different studies that has looked into how electricity consumptions is going to likely double for data center settings for this by 2030. While it is very hard to project the future, I think there are many reasons that we believe that this energy growth trend is going to continue. So today, since we are looking at this new application use case of AI, generative AI technologies, I want to sort of give a very high-level overview on the important phases that we usually go through in the AI development cycle. At a very high level, there are 4 major phases in the AI model development cycle. We often start with data, and then we spend a lot of time on extracting valuable features from the data set itself, which we call the data processing phase. Then once we have the data set in hand, the features that we know how to develop a machine learning task, we go into the experimentation phase. This is where machine learning researchers sort of experimented with different modeling techniques to get ideas about the potential of the particular innovation. Once we have a good idea about the modeling technique, we go into the production training phase. This is where we scale up the model, the data set sizes, and we usually train the model with much higher volume and much higher quality data. Then, when we reach the particular accuracy target that we have in mind, we further optimize the model for deployments. And this is when we take the model to make trillions of inference to support a variety of different products at Meta. If you take a look at a particular model and start examining the resource allocation, in this particular case, power capacity allocation across these different phases of the model development cycle, what we found is that for this particular recommendation model that we have studied, the amount of power allocated to the data processing, ingestion, and the training phase versus the inference phase is about 1/3. And what this means to us is that if I care about performance efficiency optimization or energy efficiency optimization, it is equally important to look at how I can make the data processing phase a lot more efficient, and as well as for the training and inference phase. So that was the case for the particular recommendation model workflow. If we were looking at then the growth trend across the different dimensions, back in 2019-20 timeframe, we did a pretty interesting study, and that was the start of our green AI journey. We started looking at the growth trend of data, model sizes, and training capacities, inference capacities, and meta. And this is what we found. In between the 2-year time frame, we see the amount of data that is used to train production models to already doubled. And in order to learn the valuable information from the increasing size data set, the model size has to increase as well. So within that the same time period, we see the corresponding model size to increase by 20 times. And all of that translates into growth in training and inference infrastructure capacity as well. Within that time frame, same time frame, we see the amount of training and inference accelerator to increase. And now fast forward, these growth trends are something that I continue to observe for hyperscale computing. The next thing in our green AI journey is that we wanted to understand what is the environmental implications, having seen the significant growth trend of machine learning and translate that into different dimensions of IT hardware equipment. And so before we take a look at the sustainability implications, I want to sort of spend some time to talk about the methodology that we use. And here we'll spend some time on the greenhouse gas protocol or the GHG protocol that you may have come across. So here, a little bit about GHG protocol. This is a pretty common methodology that companies will use to understand their own environmental emissions. And this is a protocol that has been around for quite a while. And most recently, it was updated in 2015 on sort of updating particularly the scope 2 emission guidelines. But at a very high level, there are 3 categories of emissions in this GHG protocol. First is the scope 1 emission. This is what we call the direct emissions. So now from a data center operator's perspective, this is the direct emissions that's produced on premise in the data center facility itself. So for example, data center usually have their backup power generators. If the generator is powered by, say, diesel fuel, and during the power blackout period, data center operator will have to activate that backup generator. Those are the scope 1 emission captures those. Whereas there's scope 2 emission, these are the emission that we call are the indirect emission. These are the emission that's produced during electricity use, where the electricity used by data centers are often generated by the power grid. And so depends on the generation type of the electricity at the power grid level, there is the scope 2 emission that data center operator will adopt. And then there is the scope 3 emission, which we call the supply chain manufacturing emission. These are the emission that is produced during the manufacturing phase of equipment. So these are, for example, the manufacturing emissions that's incurred during the manufacturing phase of the CPUs, the GPUs, the memory and storage equipments that happened at the manufacturing phase. It can also include data center construction emissions as well. And the scope 1 and scope 2 emissions of data center often is what we call the operational carbon footprint for workloads that's running in data center, whereas the scope 3 emission is what we call the embodied carbon emission. These are the carbon emissions that are embodied in the computing infrastructure. So the CPUs, the GPUs, or the data center constructions, for example. So maybe I can pause here a little bit to see if there are questions before I proceed.
Yes.
Yeah.
Hi. Nice to meet you. Sorry, I was a little bit late logging in. I wanted to ask, like the scope 3, is this estimated over per year? Because, you know, you always buy new ones and you throw them out. They have a certain lifetime. How is this calculated?
Yeah, happy to elaborate more on this. So this will depends on what characterization results that we are looking at. So if we go into company level sustainability report that is often released on yearly basis, the scope 3 emission will include all the emission from manufacturing that is incurred during that particular year. if we look at scope 3 emission, or in this particular case, the manufacturing emissions in life cycle assessment report, then that is the emission that is happening, that includes for the entire life cycle of a particular product. And depends on what is the sort of estimated life cycle or lifetime of the product, this embodied emissions can be amortized across year of use, which I can elaborate, which the rest of my talk will cover a little bit more.
Thanks.
Cool. So that's on the GHG protocol. So as I mentioned, in our Green Air journey that started about 2019, 2020 timeframe, one of the key questions that we were very curious and somewhat worried about is what is the carbon footprint of large model training? And there was, at the time, there were a lot of conversation, in particular in the machine learning research community. And instead of sort of take the estimates that was done externally, a couple of us felt like we have an opportunity in hand by looking at instrumenting the production training workflow that we have at Meta. And this is what we found when we delved deeply into understanding the estimated carbon footprints of production model training back then. So on the x-axis, we are looking at 6 most important machine learning models at the time, ranging from language model that's based on transformer model architecture to a wide variety of deep learning recommendation models. And on y-axis is our estimation of carbon footprints. And what we found is that training a modern language model back then for Meta product will produce 45 metric tons of carbon emissions. Just to put that into the context, that is equivalent to 5.4 homes energy use for 1 year. And that's based on US household statistics. Training a DLRM, deep learning recommendation model, will produce carbon emissions that's 9 times higher in this particular study. Now, once the model is trained, it will be further optimized, as what I mentioned, for production deployments. So we also look at all the additional operational carbon footprints coming from the inference prediction phase. Depends on what machine learning task that we are looking at. Inference footprint can add 1 to 2x more emissions. And this is the carbon emissions that we characterize for the particular model's life cycle. Once the model, and I guess take recommendation model as an example, these are models that's trained on current events. So these models will need to be retrained periodically. And so you can imagine that this is an iterative process. And in data center fleet, there are many, many different models that will be trained and will be serving inference simultaneously. And then I guess as what I alluded to, there is also the embodied carbon, which we learned and start looking at the time. And to look at embodied carbon, I guess we will have to look at the sort of manufacturing phase of a particular computer systems. So in this particular example that I'm going to show, we are taking this methodology called life cycle assessments, or LCA. This is also a pretty common methodology that industry use to understand the where carbon emission is coming from for a particular product. So there are 4 phases in this LCA analysis. There is manufacturing phase, there is transport, which once the product has been designed and produced, it will be transported into, say, for example, data centers, and then we'll turn on, I guess, the IT equipment for product use phase. And then once we reach the end of life for the product, it goes into the recycling phase. So taking data center as an example, manufacturing emissions will include wafer manufacturing and how the wafer is diced into different dies. It will include emissions that's incurred during the packaging process, and then eventually they get assembled into data center servers and racks and and start running training workloads. You may have come across articles as such that talks about how significant the manufacturing emissions can be. To us, I guess, when we started looking into this emission characterization, we went into many different publicly available sustainability reports. And in this collaborative studies with colleagues from Meta and researchers from Arizona State and Harvard Universities, we started quantifying where emissions can come from in this work called Chasing Carbon. In this particular pie chart, we look at many Apple's sustainability reports, and Apple did a very good job on characterizing and sharing their products emission data. And this is what we found. Across all the Apple product, we found that hardware manufacturing accounts for 74% of Apple's overall emissions. And what is quite significant is the emission that's coming from integrated circuit manufacturing, and that includes the application processors, the DRAM, and the NAND flash storage devices. All that in combination is 33% of Apple's product emissions. In comparison, the product use emission is only 19%. And if you sort of delve deeper into these numbers, it kind of makes sense from computer architects' perspective, given that these are battery-operated devices, and oftentimes the energy efficiency during the product use phase is quite high. And most of the time, these hardwares are actually sitting idle, right? And so when we look at the product lifetime, we quite expected that the emission is going to be dominated by embodied carbon, especially for consumer electronics. Going forward, beyond mobile computing, I guess, we expect the next wave of computing devices to be wearable. So for example, Meta has partnered with Ray-Ban to roll out smart glasses already. And we would expect very similar embodied and operational carbon footprint breakdown, just like what we're seeing for Apple's consumer electronics. And these smart glass devices come with pretty high-end accelerator already. So tomorrow, when we have a very advanced augmented reality wearables with contextual AI capabilities, we should start thinking about how all the accelerators is going to come with all the additional embodied carbon. And we have a quite exciting opportunity to start thinking about how to optimize that with carbon in mind. And on top of that, I guess there's also all the additional data centers that would need to be built in order to power these smart IoT devices that each of us is going to leverage in the near future. I'll pause here before I go into the next part of my talk, which I'm going to talk about some of the things I believe our community should focus on in order to think about sustainability for computer system design. Are there questions? Okay, so I guess I'll move on. Oh, okay, I guess we have a question from Mikhail.
Yeah. I would like to ask you if you have looked the sustainability from the perspective of water, embodied water consumption in order to create all the hardware, and the water consumption of the energy sources that produce the energy that the data centers are using.
Yeah, good question in the sense that I have come across studies that looks into for example, to purify water, sometimes it will incur additional electricity, and therefore those sometimes can be characterized as the embodied emissions or embodied electricity in water that will subsequently be used for data center computing or producing electronics, for example. What I do not have top of my head is how significant that is. But one thing I'll mention is that there is this IMAC net zero tool where they started looking into the embodied carbon that goes into water required in the semiconductor manufacturing process. And this particular tool, there is a public version. And if that's something that you're interested in delve deeper into, I think there's a lot you can find out over there.
Could you repeat the name of the tool, please?
It's called IMAC Net Zero.
Okay.
I'll have a slide towards the later part of my talk. And so hopefully that gives you a pointer.
Thank you very much.
Sounds good. Jonathan.
Hi. Thank you for, when I was looking at the inference consumption cost, I was curious if you're aware of any work that looks at sort of time of day and optimization of inference with respect to consumption of CO2, because not all data centers are emitting at the same rate all the time, right?
Yep. Yep. Great question. The question is more on when we start looking at carbon reduction or optimization, have I looked into optimization across the time dimension? As what I'll mention later part of my talk, we had a research project now a few years ago that looks into this particular direction. And I'm also happy to share why that stays as a research project and not something that we push forward subsequently.
Thank you.
Yeah. Shubham?
Hello. Thank you for the talk. I'm gonna go there. So I have a question about one of the slides where you showed the different DRMs and their carbon usage. You showed for the training and for the inference. Does the data preprocessing, you put it with the training? Is it part of the training in your experiment?
The question is, in the carbon characterization, there wasn't a particular phase that carved out the data preprocessing part. That we include that in the training phase. For that particular study, we do not specifically carve out the data preprocessing phase. And the reason being is that a lot of the data preprocessing step sometimes happens offline. And so it may not be directly considered into the training phase. And that's going to be highly dependent on the implementation of the workflow.
Okay, I see. Thank you.
And you can think about how a lot of data set will get reused for different training flow. And that sort of data preprocessing phase could be amortized if we end up caching the data set itself.
Mm-hmm.
Yeah.
Thank you.
Cool. Let me proceed to the second part of my talk. So I guess what we have seen is the carbon characterization analysis for computing across the life cycle, and we've looked at the AI model development cycle. We've also looked at across a particular consumer electronics lifetime. For the next part of my talk, I'm going to share sort of my thoughts about where computer architect or system designers can do to help improve sustainability of our computing devices. And I boil down to 4 directions that sits in the intersection between AI, system, and sustainability. So first, I think we have a pretty exciting opportunity to make AI a lot more efficient than it is currently is. Second is that AI as a workload is already quite flexible, and it can be made and designed to be a lot more flexible, which is going to help us sort of perform something that we call demand response, basically between the consumers of electricity and to the electricity provider interface. It turns out that AI can also be part of the solution space, which many of my colleagues at FAIR are looking into. And we have a research project in this particular direction as well. And then finally, to tackle the rising ratio of embodied carbon for especially consumer electronics, I think there is a lot of interesting research direction that we can tackle by making AI hardware to be much more carbon efficient and comes with much lower embodied carbon. So to start with, let's look at what I mean by optimize for efficiency for AI. The first step for making AI efficient as a computer architect, I guess how I look at this problem is to understand where compute cycle is going in your workloads. And in this particular case, when I started looking at where computing cycle is being spent fleet-wide, I guess what we found and at around 2018 is that recommendation model is actually one of the biggest consumer of compute cycles for both training and inference. At the time, if we were looking at AI training cycles across the board, about 50% of compute cycle is dedicated to training recommendation models. And when you look at inference cycle, 80% is coming from deep learning recommendation and ranking use cases. And this is in the overall context of image workloads, language, speech workloads, and all that. So as a computer architect, I guess this is the end-dose low bottleneck. If we were going to design computer that accelerate a particular class of workloads, this is the workloads that we must focus on. And this is a quite interesting problem to solve in the sense that these recommendation models come with very different system resource requirements as compared to CNN, convolutional neural networks, as compared to fully connected layer, or sometimes also known as MLPs, and like recurrent neural networks. In these recommendation models, there are many embedding tables, and these embedding tables are sometimes very large. So what these embedding tables are, it's basically taking categorical inputs, and embedding table then will project them into dense inputs, which then becomes the inputs to the deep learning neural networks. And turns out that from storage capacities perspective, embedding tables are much larger than the sort of the capacity requirements for other neural networks. From compute intensities perspective, these embedding tables compute intensity is much lower as compared to CNNs or FCs, fully connected layers, or recurrent neural networks. And so now, if we were designing AI accelerators, for example, embedding table comes with a very interesting accelerator design opportunity. Finally, if you look at the memory access pattern for embedding tables as compared to other type of neural networks, you'll find that the memory access pattern for embedding table is much sparser and also is irregular. And so this then again is a quite interesting system design opportunity. So that was sort of the scenario back then. These days, I guess everybody is talking about large language model, generative AI technologies, and it turns out that this is also the kind of deep learning workloads that is driving the design of next generation computing clusters. If you look at, ever since ChatGPT come around, various different companies are investing in quite significantly into building out AI clusters, and these are pretty large, high-performance machine learning clusters that can compose tens of thousands of accelerators in just one data center setting. But then also multiple data centers are being built in the same geographic regions. Meta itself has announced at least 2 different Gen AI clusters. Each of them come with 24,000 GPUs already. And these large language models are quite interesting in the sense that this is the new kind of workloads that's pushing the limits of infrastructure. And they are quite different as compared to DORM. Just a little bit of comparisons between these two type of training workloads. If you look at the amount of compute required to train large language model with a sentence, it would already require 1 petabyte, one petaflops of compute. And imagine that often we train a large language model with hundreds of thousands of sentences. That's the amount of compute that needs to be packed into this training cluster, right? If you look at inference phase, unlike DORM, I guess large language model inference phase come with two distinct operations. One is what we call the prefill, and the other is the decoding phase. The prefill phase is about understanding user prompt. For example, like I give this is what I would like the AI assistants to help with. And usually it's in the structure of a sentence. Now, from system design's perspective, it's quite interesting in the sense that there are all these parallelization opportunities that can be operated in the granularity of tokens. And so what that translates into is compute intensity. Whereas for the decoding phase, this is the phase where tokens is getting generated one by one. And in order to produce that response in real time for reasonable user experience, the decoding phase usually comes with very low latency requirements. And so you can think of it as a very resource expensive process, in the sense that in order to push down the response latency, we will have to throw in a lot more compute into it. So like, multiple GPUs, how do we figure out how to distribute the computations across these different GPUs in order to further push down the latency, right? So again, language model in this case is a exciting new type of workloads that we are building systems for. And so in our most recent ISCA paper, we delve deeper into understanding where time is spent. From execution times perspective, these language models come with much higher compute intensity. And so a lot more computation time is being spent on just the compute itself as compared to, I guess, communication and others. And there's a lot more overlapping opportunities between compute and communication for language model. Finally, if you are into, I guess, optimizing for performance of these large language model training, you would then care about the type of communication collectives in the training phase. And it turns out that large language models communication collectives can look quite different from the ones that's used in deep learning recommendation models. And so now this gives you some ideas about what to focus on from performance optimization's angle. So having gone through sort of workload level characteristics, I don't want to spend too much time on efficiency optimization, as while it is a very important first step, I believe that our community has done quite well in efficiency optimization and innovation. And so I just want to sort of provide pointers to some of our work in case this is something that you want to learn more about. So I can move on to some of the carbon-specific optimization work, which I believe is quite important, but much less explored, at least by our systems community. So while we look at these different opportunities for efficiency optimization, what we found with the use case of AI is we often get ourselves into this Jevons paradox situation. And what I mean by that is while we go through the efficiency optimization iterations, and we can, reduce power footprint quite a bit, sometimes in the order of 800 times, we continue to see AI's power footprint to increase in the presence of all these efficiency optimization. And this is something known as Jevons paradox, which says that when the use case demand is high, efficiency optimization will encourage more uses, leading to higher resource consumptions in aggregation. So despite the fact that we can achieve higher performance efficiency, we continue to see the power footprint of, in this particular case, the language model use case to increase over time. So what can we do in addition to efficiency optimization? Next, I want to share with you some of our work in the flexibility space. Okay, so if we can make AI computing to be more flexible, the computing infrastructure then becomes more resilient and also more sustainable. And what do I mean by that? So if you remember what I shared, these large language model training today can easily take tens of thousands of accelerators at once, and the scale is increasing very quickly. What that means is that if each of these accelerators will fail infrequently in combination at the scale that we are operating on, job failures can happen quite frequently. And this is these job failures can come from a variety of different sources. It can come from user program bugs, can come from system software, from out of memory errors that happens in the middle of a training run. It can also come from hardware failures, and that can come from, I guess, compute as well as memory side of things, right? And this is nothing particularly new. I think our system community has figured out how to build resiliency into our computing infrastructure. What I thought is interesting is that we now have this, I guess, well-known best-top curve for hardware failure. Usually at the start of our training clusters, we expect the failure rate to be quite high. But we expect the failure rate to plateau and stabilize, I would say, after the first couple of months. And then once we start, continuing to operating the computing infrastructure for longer, we will start seeing hardware failures to increase again due to wear out, thermal stress, and all that. One way that we can effectively amortize the embodied carbon that we talk about is to go figure out how we can extend the lifetime of these hardware equipments. So then what this means is that our system community will have an opportunity to figure out how do we come up with software techniques such that we can continue to operate programs correctly on top of aging hardware. So there's a lot of this type of work that can happen, and that will help with sustainability of our computing infrastructure. One of the sort of questions that I often am asked about is how bad is hardware failure in these training clusters? And so in our recent work, we did a deep characterization on understanding where job failures can come from. And so this characterization was based on 11 months of data that we collected from the research superclusters. And what we found is that among all the training job failures, the failure that's caused by hardware actually is pretty rare. In this particular case, only 0.2% of job failure is caused by hardware failure. But what's interesting is that when hardware failure happens, it can waste significant amount of resources at the cluster level. So that 0.2% of hardware failure will map to 19% of downtime at the cluster level. And that's the sort of, we went deeper into this particular work in our HPCA paper, which can sort of take a look beyond this particular talk. But if you think about the computing environment at scale, there are actually many other changing parts other than compute resource availability. Power availability can change over time. If you are looking into electricity price optimized computing infrastructures, then electricity price can change as well. Or at the same time, if you want to start looking at optimizing for carbon intensity of energy used by data centers, that also is a time-varying dimension. So how should we think about all these dynamically moving parts in data center computing? It's actually quite interesting that on workload side of things can also change quite a bit. In some of our earlier studies, we started looking into flexibility or delay tolerance of workloads that's running at the data center level. And in this particular work, we characterize all the workloads that's running in data center settings across the spatial flexibility dimensions and across the temporal flexibility dimension. And what we found is that some class of workloads are actually quite delay tolerant in the time dimension. For example, offline data processing or AI training jobs, right? As long as these training jobs finish within certain amount of time, I think the machine learning developers wouldn't really care if it finishes at 2 a.m. or at 8 a.m. So there's some inherent delay tolerance over there. Some of the other class of workloads are flexible from data center locations perspective. They don't necessarily have to be running on a particular data center as compared to other locations. And this exposed quite interesting optimization opportunity, which can align well with the changing carbon intensity of electricity generation. And if we can figure out how to sort of coordinate demand with response and respond to the particular demand from power grid operator side of things, then perhaps there is carbon reduction opportunities on the table. So I won't have time to go deeply into this particular work, which we call Carbon Explorer. I do want to put this on your radar in a sense that if we are able, now we basically propose a tool called Carbon Explorer that can enable data center system designers to understand the design space of operational carbon footprints and embodied carbon footprints. And some of the key takeaway that we found in this particular work is that to completely eliminate operational carbon footprint, it's going to be quite costly because there's a long tail. And to get rid of that long tail of operational carbon footprint, it's going to come with quite significant embodied carbon costs for the solution space that we consider. So that's something to think about. On top of that, I think we also found that a hybrid solution that looks into combinations of renewable and energy storage, as well as computation shifting, usually give you the most cost-effective solutions to reduce operational carbon for data center computing. We open sourced the tool, and also the paper has been published at ASPLOS 2023. So encourage you to read more about this work and see if there is any additional opportunities that you can build on top of this pretty awesome tool that we put out there. I talk about how AI can be part of the solution space, but I won't have time to go deeply into this. If I'm happy to have additional conversation because I do want to spend time on this embodied carbon reduction direction. So remember in the GHG protocol conversation, there is this scope 3 supply chain manufacturing emissions. And this particular components can be quite significant, especially for consumer electronics. So what can we do in this particular direction? Just to sort of give a high-level idea about how significant embodied carbon can be. If you take a look at the operational and embodied carbon ratio for two generations of iPhone 3 that's released in 2009, and compare that with iPhone 11 that's released in 2019. So basically by 10 years apart. What we found is that Apple does a really good job on improving the energy efficiency for their iPhones. We see a 1.6 times improvements in energy efficiency, but that is coming with a 3x increase in embodied carbon. So these are coming from all the additional accelerators that get incorporated into the newer generations of iPhone devices, right? In fact, if you look at the die area photo for the A14 or M1 processors, you will see a significant amount of die area is devoted to the neural engine or the AI accelerators. And these are where all the additional embodied carbon emissions can come from. And this is why I was really excited when we started developing this architectural carbon modeling tool, which we call ACT. At the time, our community didn't have design tools that can enable carbon-driven hardware design. And so with my colleagues, Uday Gupta et al., we started looking into how to build a carbon modeling tool such that hardware designers can design hardware using carbon emission as an estimate, and then along with performance, latency, power, and area costs. And ACT is our answer to this direction. We take this architectural carbon modeling tool to approximate embodied carbon and operational carbon given fabrication manufacturing characteristics, given the workload software characteristics, given the hardware design that we want to consider. And then this embodied and operational carbon then go into our hardware design space exploration. And then we can then now start thinking about how to incorporate carbon in the overall hardware design flow. With ACT, we can now look at the balance between general purpose processors with application-specific accelerators in a more systematic way for the workloads that we care about. We also look into the fault tolerance aspect for hardware software co-design. We started thinking about how modular system design can help tackling the different failure characteristics of different like logic or memory or storage requirements. And we also then open source the tool, which our communities can use the tool to explore this design space in a more systematic way. Here is the paper that was published at ESCA 2022. And subsequently, we extend this work to look at extended reality systems. And a newer version of the work was just published at HPCA this year. Within Meta, ACT is also influencing the way that we quantify Scope 3 embodied carbon emissions. So here is a snapshot of Meta's sustainability report from 2024, where we talk about how internally we are building internal tools to quantify the embodied carbon of millions of instances of IT hardware equipment in the data center fleet. In addition, Meta is also part of this IMEC program called Sustainability for Technology and Systems program. And the idea here is to build a tool that is based on research fabrication technologies that IMEC is looking into, and to enable this tool for all the industry members to advance sustainability from hardware design or many other dimensions, circuit designs, green manufacturing, so on and so forth. And so that's a pretty exciting effort that I want to put on your radar. There is a public version of the tool that you can use. But at the same time, I guess, IMEC is improving the tool in parallel, and also Meta and other companies like Google, Amazon, Apple are devoting quite a bit of time for using the tool and using the tool to quantify internally the sustainability implications of computer systems. Now, with the ACT framework and potentially also with the IMEC tool, we can carry out a lot of very interesting carbon analysis given specification of particular hardware. For example, we can take the tool to understand carbon analysis for a variety of hardware like NVIDIA's GPUs, Intel or AMD's chiplet-based architectures. We can also do a lot of what-if analysis by taking an actual GPU implementation and start looking at how to meet the same performance level, but if we were able to look at a chiplet architecture instead. Internally, we are doing a lot of these type of exploration analysis to understand how a newer architecture can bring in us additional carbon reduction potentials across different architecture design points. Another quite interesting use case is to look at how to use the carbon analysis to determine the optimal hardware refresh cycle. For example, taking the 3 generations of NVIDIA GPUs, we can take the current workload operational efficiencies across the different generations of the GPUs to understand the optimal refresh cycle that minimizes life cycle emission. With a different operational to embodied carbon ratio, now more dominating by embodied carbon, our tool tells us that we should wait at least a year before we refresh GPU hardware. Now, if embodied carbon becomes even more dominating with the 1:10 ratio, then our tool then will tell us that we should skip a generation because now the optimal refresh cycle for total carbon optimization is longer. So these are like some examples of what we are doing, and I'm quite excited to see many other subsequent work that has happened ever since we started this journey. Let me conclude my talk, but I'll provide the slide deck in case you want to learn more about all the additional work that we have done. So to recap a little bit, in this talk, we started looking at carbon footprint characterization through the lens of AI, but there are many other computing workloads I think we can focus on. And I also share 4 very important directions that I think our community and our industry should focus on. That ranges from efficiency optimization, how do we make the computing infrastructure to be more flexible, to encourage demand response optimization between data center and power grid operator, how AI can be part of the solution space, and then also embodied carbon optimization. I think there are a lot of tools that has become available since then. The ACT tool that I talk about, Carbon Explorer. There's also the AI Energy Score project, which is quite interesting as a way to provide model developer a way to quantify energy consumptions of AI models. And with all these tools and the newer metrics, I think this is a very exciting time to work in the system community in the sense that we should rethink about how programming language can be designed to expose opportunities for carbon optimization. There is tons of hardware software co-design opportunities. along with hardware design as well. And I think there's a lot of interesting opportunity that's just sitting in between the computing and sustainability space. Thanks so much for your time. Big shout out to my collaborators and colleagues who I get to work with during this journey, and a lot of work that I get to share with you are conducted with my amazing colleagues at Meta and in academia. Thanks so much. Perhaps I can take a few more questions if there is time. Okay.
Thank you. Thank you for the great talk. So I see one hand up.
Yep.
Yes.